In this lesson, we shall focus on mathematics, MAT2615, calculus in higher dimensions. We shall look at double integrals, limits of multivariable functions, and a lot more. And we proceed as follows. Right, L1 and L2 are lines in R3 that both contain the point 101. L1 is parallel to the vector 241. And L2 is parallel to the vector 3, 1, minus 1. Find an equation for the plane that contains both the lines L1 and L2. All right. Now, to do this particular question, we need to find the normal to the plane. So we note that the normal to the plane, is given by, right, it is given by exactly 2, 4, 1, 3, 1, minus 1, I, J, K. Now the vector 2, 4, 1 is put here. 3, 1, minus 1 is put here, like so. Right, and we compute this determinant here as follows. The unit vector I, we multiply 4 times. Minus 1, you get minus 4 minus 1, minus 5. So which is minus 2 minus 3 minus 5. Right, and we block this row in this column, we get exactly 2. 2 by 1, it's 2 minus 12. And 2 minus 12 is minus 10. This can also be written as minus 5. Okay, let's first do some simplification here as follows. So this equals minus 5i plus 5j minus 10k, which is minus 5 minus 10, like so. And this is the normal to the plane, right? In other words, L1 is parallel to the vector 2, 4, 1, and L2 is parallel to the vector 3, 4, 1. You need to find an equation for the plane that contains both lines L1 and L2. And therefore, we find the actual vector Cartesian product of the two, or the vector cross product, right? The vector cross product of the two vectors, which are 2, 4, 1 and 3, 1, minus 1. Therefore, the equation of the plane is given by the equation. Right, so the equation of the plane is given by, right, so the equation of the plane is given by the following. So we're going to take an arbitrary vector, x, y, z, minus a point, 1, 0, 1, dot the normal. In other words, now, if you take the arbitrary point, x, y, z, with actually the point 101, because L1 and L2 are lines in R3 that both contain this point. So this point is a point on both lines. But now if you then say this point x, y, z, and we minus the x, y, z minus the point 101, we get a vector that is on the plane. We actually therefore realize that if you look at the geometry that arises from this, a plane here, and you then have a vector that is actually the normal to the plane, and therefore it is perpendicular to the plane and perpendicular to a vector parallel to the plane. Okay, now we continue.
Yes.
All right, so we're 5, 5 minus 10. Now, the dot product of actually a vector perpendicular to the plane and a vector parallel to the plane is actually 0 because the vectors are orthogonal. A vector parallel to the plane and perpendicular to the plane are orthogonal vectors and therefore have 0 dot product. And this, as a consequence, yields the following. So we have here x minus 1, and then we have y, and then we have z minus 1. And this is minus 5, 5 minus 10 equals 0. Now, computing the dot product to obtain the following, right? Minus 5 times, so they have minus 5 times x minus 1, which is z minus 1, minus 5 plus 5, okay, plus 5y minus 10z plus 10 equals 0. Now we analyze this and check very, very carefully, and we're able to see by simplification what the answer is going to become, meaning we have exactly y. Okay, if we add everything here, you would have exactly the following. Let's start by the proper addition here. And the addition is going to be exactly minus 5x. So we're done with the x term. And then we have plus 5y minus 10z, which is equal to minus 15. So divide by negative 5. And if you do so, we get actually exactly x minus y plus 2z is equal to 3. And this becomes the answer. So able to get x minus y plus 2z equals 3. And this is equal actually exactly the equation for the plane that contains both lines, right, L1 and L2. So we have solved this problem here. And it is our hope that this is very, very clear and therefore is very much well understood. And we proceed as follows.
Yes.
Okay. Now the next question is a recap on the notion of limits and continuity. Now show that this limit does not exist. Right, to show that this limit does not exist, we proceed as follows. So we consider the curves. Consider the curves. Curve 1 given by y equals x, and curve 2 given by y equals x to the power 2 out of 3, x greater or equal to 0. Consider the curves. Curve 1 given by y equals x, and curve 2 given by that. So with the limit.
Can you remind me how again do you find your curves?
Right, okay, so the curves are chosen such that you choose any arbitrary random curves that actually pass through the limit. So they pass through the origin because x and y approaches or tends to 0 and 0. So the point surely y equals x. If this is our Cartesian plane, it is clear that this is our y and this is our x, and the line y equals x passes through the origin. And therefore, it is said to be what you call a relevant. It's said to be a relevant curve. Right, so, but also we choose this curve here, and this curve will also, whenever x is 0, y is 0, so surely this curve also passes exactly through the origin there. So both curves indeed are relevant curves. And we have chosen the curve, yeah, we've chosen both curves. Yeah.
Hello.
Yes, please.
The curves, regarding the curves,
Yes.
like where do we find the function of the curve? You just mentioned the limit telling us about it passing from to 0 to 0.
Yes.
What about this y over 3 and x over 2? Like, what
Yeah,
about them?
yeah, the y equals, for instance, y equals x to the power 2 over 3.
No, the one on the
Question.
the function that
Okay,
we
the
should show,
limit of
it
y
has a limit.
cubed over
Yeah,
x
that one.
cubed and xy approaches 0 and 0. You're saying this one? Yes. So yeah, we don't look at this in the meantime, quite. We actually look at the fact that we need to just choose relevant curves that we're gonna substitute into this function. But obviously, these curves must pass through 0 and 0. Any random curves. But now these curves are called relevant curves. Okay, but they pass through 0 and 0, like the line y equals x. It's a line that passes through 0 and 0. And therefore, this y equals x is a relevant curve C1. And also the curve C2 is also relevant curves that passes through the origin, you know? So yeah, are you saying you expect us to sketch this one, the y cubed over x squared?
Yeah, I thought you were going to use those two.
Yeah.
I
You
don't
see,
know how.
yes, okay, yes. There's a hint. You see, like in the choice of this particular one here, the choice of y equals x to the power 2 over 3 is such that it has been chosen such that when you replace y by x to the power 2 over 3, the 3 is going to cancel. So you have y cubed in the denominator and x squared. And then the y is this. So the y is x to the power 2 over 3. And then you cube it. Okay. And therefore, this is x squared over x squared. Right. So in the end, you'd have therefore that this is chosen, the fraction in the top is chosen to cancel with the 3 here. So that is how you can actually use the function itself to sort of choose curves that are going to work nicely and are not going to give problems, and that are going to simplify beautifully. Like this one simplifies to 1, as we shall see very shortly. Okay, we right back to the question. And right now, we then have this one. So we're going to therefore realize that this is equal to, for example, the limit is the xy approaches the origin along the curve C1. Okay, along the curve C1, it's this one, y equals x, meaning that wherever there is y, you're going to put x cubed over x squared. Okay, so you can obviously now realize that you have x, and then the place of y, you can also put x. This obviously happens along the curve C1. And then we have x cubed over x squared. What is x cubed over x squared? It's just x like this. Right. So now what you can do here is to take the limit, and therefore this means x approaches 0. And then it is the limit of x. But the limit of x as x approaches 0 is actually exactly 0. Okay, so that sort of gives us one part of the limit. Simultaneously, we have the limit as xy approaches 0 and 0. You have y cubed over x squared, which is the limit. Now you're going to actually evaluate this limit but this limit evaluated along the curve 2, right? Curve C2. And this means that you have x in the place of the y, you put x to the power 2/3. And this approaches the origin. And then in the place of the y, you put x to the power 2/3 and you cube everything. The denominator remains x squared, which becomes the limit. So now this one is still along curve 2, but as this approaches 0, then it means that x approaches exactly 0. Now the 3 cancels here, giving us exactly x squared over x squared. So which is the limit as x approaches 0 of 1, and this limit equals 1. Okay, so you can see that 1 is 0 and the other one is 1. Right, so in other words, we come and then say hence the limit of xy of 0 and 0 of this one. Okay, let's use a different color. Let's use green. Right, so it follows therefore that this limit here, as xy approaches 0 and 0 of y cubed over x squared, is equal to the limit of over the curve C1 is the limit as xy approaches 0 and 0 along curve 2, and this is y cubed over x squared. It's not equal. Okay, so you are able to see that these limits are not equal to each other because along curve 1 to 0, along curve 2 it is 1, and therefore we can actually say the limit. Right. Therefore, the limit does not exist. The limit does not exist. Right. So any question there?
No.
Okay, no question. And move forward to the next one. Let's look at number 3. Right, in number 3, what we have is the following. We actually have to write down the integral below as a sum of double integrals in which the order of integration has been reversed. Do not evaluate this integral, but now we're going to focus on double integration. And also we shall spend time on triple integrals as well. Right, so now if you look at these, the questions, how do you write down the integral below is a sum of double integrals in which the order of integration has been reversed. Okay. So which means that you have this one here. All right, now this one is the graph of, for example, so now we know that the two curves, right? So the two curves, y equals x squared and y equals 4 times the modulus of x are drawn below. Right, so now let us draw them here.
Are we
Yes.
reversing this double integral
Yes, we're reversing the double integral. Yes, please. But we
to what? To do a
Please come
single
again.
or
Okay, yeah, reversing, we're gonna, because now it is dy dx, so reversing, we're gonna make it dx dy. Okay, so that is the objective. But obviously we're gonna analyze the two curves, right? So we're gonna focus on the curves y equals x squared and also the curve y equals the 4 times the modulus of x. Simultaneously, there are a couple of things to regard here if you look at the region of integration, because whatever we have here is that we have this particular double integral, but we need to reverse the order of integration. So if we have this double integral from -4 to 4, x squared to 4 times the modulus of x, 2x plus y dy dx. Right. So now you then say our x therefore lies between -4 and 4. Okay, these are sort of the limits of integration. So if you then say our x therefore lies between 4 and 4, simultaneously our y lies between what? Our y, because there is dy here, lies between x squared and 4 times the modulus of x. And this is sort of, these inequalities describe the region of integration over which we are performing this integral here. Okay, so we therefore proceed as follows. Now, looking at this particular integral here, we note that this is the curve y equals x squared. Y equals x squared that has been drawn. But you also have y equals the modulus, 4 times the modulus of x. Okay, so it's just the same as the absolute value function, but just multiplied by 4. So you have something like this. And therefore, this one, the line here becomes exactly y equals 4 times the modulus of x. So continue. We continue.
No.
Please come again.
No, I'm still reading the graphs.
Oh, okay, that's fine. Right, so this is sort of what we have. But also, it becomes very important to be in a position to find the points of intersection. So we note that the graphs intersect where x squared is 4 times the modulus of x. And this means that x squared minus 4 times this equals 0. Or we can first write it as follows to simplify matters. We can just square both sides. We can square both sides, getting exactly x to the 4th power equals 16x. Which means that, okay, which is 16x squared. Take out x squared as a common factor, getting x squared minus 16 equals 0. This means that x is 0, or x equals plus or minus 4. So this is sort of what we're getting here. It's sort of what you're getting here. Right. And this sort of becomes the point of intersection. So now, looking at this here, we're able to see that y is 0 here. X is 0, y is 0. Y is 16. Okay, whenever x is 4, y is 16. Whenever x is this, y is 16. Right, so, okay, this is what we have exactly. This is the origin. Anyhow, right, so because y is x squared, or y is 4 times the modulus of x, or y is this. And this describes the point of intersection, -4 and 16, 4 and 16 as well. Okay, now we're good. And therefore, we have the effect that. So we write the following. Thus, right, so we write the following. Thus, the two graphs above intersect where x equals 0 or x equals plus or minus 4. So R is split into region 1 and region 2. Where? Once again, this discussion is recorded. So you will receive the recording at the end of our discussion. So it's split into 2 regions. Okay. So you have this. And then, okay, let me just try to draw this carefully. So you have exactly this one here and this one there. Y-axis and the x-axis. This point of intersection is -416. 416. Okay, and then this is the origin. Okay, now we'll look at region 1.
How did you get the line on your left?
This line.
Yes.
Okay, this is the absolute value graph for y equals 4 times the modulus of x. It's straight lines like this. So it forms a V. And obviously we have y equals x squared, which is the parabola. Okay, so that is sort of the reason. So the parabola has the equation y equals x squared. And this one has y equals 4 times the modulus of x. Like that. Okay, so the absolute value function forms a V. And the parabola is like that, you know? Okay. Now we continue. Now there's
Yes.
therefore region 1. So this is split into 2 regions. Region 1 and there's also region 2. Let us describe region 1 in set builder notation. So region 1 can be described in set builder notation where the xy is actually a member of R2, such that our y, right, our y would begin from what y is here, because this is x and y. So y starts from the origin to the highest point. The highest point is 16, at both points of intersection. So in other words, our y, therefore, will lie between 0 and 16. Our y lies between 0 and 16. What about our x? Right, so now our y lies between 0 and 16. And our x between 0 and 16. And our x, actually now, because there are 2 regions, Right, for this first region, region 1, what will our x be? So let us work it out. So now to work it out, we'll be able to see that, for example, our y is x squared. If our y is x squared, it means that x is what? If you take the square roots, which means that it is plus or minus y, square root of y, x. Okay. So y, therefore, it's x is plus or minus. So in other words, you therefore have that x is minus the square root of y this side, and then x is the square root of y on the other side here, and then y is negative the square root, because x is negative the square root, because x is negative on the left. Meaning therefore, here we shall put minus the square root of y, and then what is x? What is x on this other side? All right. So in other words, obviously we are describing region 1, please. We're still describing region 1. Region 1, our x is 0 here, or our y rather is 0 to 16. Our x now, and now your x would be, in what way would the x be actually studied? So you can see, therefore, that our x would be from minus the square root of y to whatever x is here. What is x there? So x would be minus 1/4 y, like that. Okay, the reason being, y on this side, this absolute value function, y equals 4 times the modulus. This side, this line here, the absolute value function is described by 2 lines, but this is going to have a negative slope here. And the other one is going to have a positive slope. We're coming to it, so that if you make x a subject, you get minus 1/4 y, like that. Okay. The other region. We can describe region 2 in the same way in set builder notation, where we have x and y in R2. Okay. Right. So if your y is between 0 and 16, okay, and what is your x? Okay.
Is it positive square root y?
Okay, that's a good question, because now we're describing this one here. Well, thank you so much for trying. And I want to mention that the way we see this is by imagining sort of vertical lines that pass through the region. Vertical lines that pass through the region. I know that maybe that color is dark, and then the vertical lines that will sort of pass through the region like that, and then there's a vertical line that is going to pass through the region, and we sort of imagine those. For example, I will reiterate on region 1 first. That, for example, we realize that our y would be this vertical line that is going to pass through the region. It's going to actually run where y is going to run from the origin to 16. And x, therefore, is going to run from what to what? Your x is going to actually run from the square root, negative the square root of y to minus 1/4 y, which is this line here. And now the other one would be this one. So obviously this vertical line is going to It's going to penetrate the region from the bottom to the top. That is why even here we start with the square root. We write them in order, because if a line passes through the region, it's going to penetrate the region from the bottom. The bottom is the curved section, which is the parabola section with the square root, and the top section becomes the straight line section, which is minus, obviously, there. Okay, but obviously now when you look at this, you're on point. Is it going to be the other square root? Let us analyze that very, very carefully. Right, let us analyze that very, very carefully. I want us to pause to reason these very cautiously as follows. Right, in terms of, because there are different ways of describing these particular regions, but I'm going to first write that the integral given, which is this one here. Right, so you have the integral from -4 to 4, the integral from x squared to 4 times the modulus of x, 2x plus y dy dx. And this integral is equal to what? Okay, let us check this out. So in other words, there are two integrals or types of integrals where the order is reversed and where the order is as given. Now the given one here, how was it obtained? And I want us to pause to reason carefully here, because that is where the correct answer is. So this one, how did the examiner get these limits of integration from this region? So this examiner first decided that, you know what? I'm going to describe this region by vertical lines that arise upward, and we say, therefore, you fix x. So the examiner sort of fixed x. If you fix x, x is from -4 to 4. You fix x is from -4 to 4. You fix x is from -4 to 4. And if you do that, then y, it's going to become what? Y is going to run from the lines that go to the top, will penetrate the region through the parabola and exit through the absolute value graph that is formed by the V shape with the straight lines there. Now, what we do is we then change the modus operandi. We change the language. We now look, because it was in the direction of increasing y. In the direction of increasing y, x is fixed. Now we're going to take the direction of increasing x, like this. Okay, so increasing x is from left to right, because x is 0 here at the origin, and then x up is positive on the right, but also x is negative on this side, and it becomes positive when you move to the right. Now, therefore, with this mentioned, we then are able to then say, if we migrate horizontally like this, we agree that still our y will be between 0 and 16. And our x would be from negative the square root to the -1/4 y for the region 1. Okay. And then now we simultaneously now analyze region 2. Okay, this one is region 1. This one. Okay. Now region 2 is the other one. So how will we enter region 2 then if we migrate horizontally? This arrow is going to first penetrate the region through the straight line. So it's going to be 1/4 y less than or equal to x. And then it's going to exit through the curved section, which is the parabola section. But now the parabola section is actually having a square root now, when we make x the subject, when we are looking for the x limits of integration. Now, which means we are in a position to use these two regions. So the integral, therefore, sort of anchored and performed over these two regions. Region 1, we're gonna write the integral like this. The integrand, right? The integrand, this one is the same. 2x plus y, so we write like this. This one was dy dx. Now we reverse the order, it becomes dx dy, and then we add, and then we put the double integral like this. Okay, 2x and that. Okay, so you have 2x plus y dx dy. Okay, look. Now, if it was dy dx, now it's dx dy. Okay, so we fix y. Y is from what here? Now, if you look at the region 1, y is actually from 0 to 16 still. So y is here, 0 to 16. What about x? X is from negative the square root of y to minus 1/4 y. And then here now you come to this region, but y in this region is also still from 0 to 16. What is x? X is 1/4 y to the square root of y. Okay, so this is exactly what we have. And this is the answer. So because when you write down the integral below as a sum of double integrals, in which the order of integration is reversed. We wrote it as a sum of double integrals, but the order of integration is reversed because it was dy dx before. Now we made it dx dy. We made it dx dy, but we have written it as a sum of double integrals. So this was a single double integral. Now we have a sum of double integrals with the order of integration reversed. Any question?
No.
Okay, good. Move forward. Now, we are focusing now on question 4. We are focusing right now on question 4, and question 4 is clear. Let D be the region in R3 below the plane Z equals 2 and above the surface. So below the plane Z equals 2 and above the surface, x squared plus y squared minus 2. Make a 3-dimensional sketch of D. Make a 3-dimensional sketch of D. Okay, let's look at 4.1. And we want to sketch these graphs. How do you sketch a graph of Z equals 2? And also, not only Z equals 2, but D is the region in the 3-dimensional space below the plane Z equals 2, but above the surface Z equals x squared plus y squared minus 2. Okay, let us draw the graph of this. So we remember that to sketch this one, we need to have the 3-dimensional space. Z, y, x. Now, if the z is x squared plus y squared minus 2, right, so this one becomes what we call a paraboloid. Right, it is called a paraboloid. Paraboloid, okay? And therefore, this paraboloid, it's going to be such that whenever x and y are both 0, z is going to be negative 2. So z is negative 2 somewhere here. And then this graph is going to be like a parabola, but it's going to be like this. And then it's going to go on and on. But on its way up, it's going to meet the plane because it's supposed to go up. It's a parabola in 3 dimensions. So it's supposed to go higher and higher and higher and higher. But instead, they are saying they are let D be the region in R3 below the plane. So there's a plane Z equals 2. So there's going to be Z equals 2 here.
You know, sir, I don't know how to
Yes,
sketch these graphs because I'm always
yes,
confused
I understand. Yeah,
about
so yes, so we need
their
to
nature.
their nature, yes, and how this sketch. So we need to we'll discuss curve sketching at some point and make it sort of a subject of our lesson to make sure we focus on just how to sketch the curves in the many different ways. But now you'll be able to see therefore that this paraboloid is like a parabola, which is the parabola would be like even in z equals x squared. Okay, z equals x squared would be in the zx plane where we remove the y-axis, and then now it's going to be a parabola that is, so even this parabola is in many ways like that, but now this one is in all the planes because there is z, x, and y, so it is in all the planes, and you can see it is also here, and also it is on the other side. Right. But now, obviously, I mean, we understand that by and large, it is a three-dimensional formation, but it is like a vase. Okay. So if you look at a vase, etc., that is used in the kitchens to keep flowers and things like that. But yeah, that is the, sort of the shape here. So this paraboloid is going to be like that, but it's going to have its minimum point at -2, where both, because now to find the z-intercept, you make both x and y 0. And when both x and y 0, then you get the z-intercept. And therefore, z is going to be -2. And you plot it there. And therefore, it will have a minimum vertex. Why is having a minimum vertex like this? The reason is because of the fact that it's how we taught in school. And obviously, you can see that from grade 10, where these graphs are introduced in the curriculum, you realize that the graph that is like this in grade 10, it's the y equals x squared graph. Obviously now there's a graph that is like this. The graph that is like that is y equals minus x squared. How do we know? Obviously we use tables. We use the table of x and y values. Like for this one, you want to put -3 or -1, 0, 1. And then now you put whenever x is 0, y is 0. Whenever x is -1, you have 1, 1. And then you plot here. Whenever x is -1, y is 1. And then whenever x is 1, y is 1. Right. And then now you plot these points. And by dint of these points, then the graph is like this. So this is the same, but now we translate these to a three-dimensional setting. In the three-dimensional setting, the truth is that to sketch this one, you need to sketch it in stages. You take a given plane and now, for example, to sketch this one, you'd have to say, I want to focus on like the ZX plane. Okay, or if you focus on the XZ plane, right? When you focus on the XZ plane, you remove Y and you forget about Y, and then say, okay, Y is not there, then you're gonna have Z equals X squared -2. And then even when you are in the XZ plane now, you make X 0, then Z is gonna be -2, and you plot a point. And what would the coordinates of this be, for example? Okay, we still can be able to find the coordinates of the points of intersection here, or the intercepts with this axis, because now you can then say, what is the intercept here? The intercept here is going to occur in the equation z equals x squared plus y squared -2. How would this intercept be obtained? This is on the x-axis where both z and y are 0. So if both z is 0, y is 0, you have z 0 and y 0, then you have 0 equals x squared -2, which means x is plus or minus the square root of 2. Which means that x therefore becomes the square root of 2 here. And in the same way, you're going to realize that y becomes also the square root of 2 here. And this will sort of be the intercepts with the x and the y axis respectively. And the intercept is the z axis is going to be at -2. Anyhow, it's not a lot that you need to do. Make a three-dimensional sketch of D. This is what is expected in the exam. Nothing more and nothing less. And we move forward to the next question. Right, so in the next question, we focus on 4.2. In 4.2, we are still given z equals 2 and the surface. Okay, here what you can also do is to sketch. You can sketch. You can rather do what? Shade. Right, because if you actually have the plane z equals 2, below the plane, this is the plane z equals 2, and above the surface. This is the surface, but above it and below the plane. So you can shade like that. You can use a different color. So you can sort of shade like this. Okay, so this is surely above the surface and below the plane. Now, if then you are to then say, and also here, it is below the plane z equals 2, above the surface z equals x squared plus y squared minus 2. Express the volume of D as a triple integral using cylindrical coordinates. Right, so now you need to remember, so what I'm going to do that successfully, I'm just going to draw a rough sketch here again. Right, we remember that it is sort of like this, and then it is this way. And it cuts through 2 here, and then here it is cutting through minus 2, like this. Z, Y, X. So that in the end, this is the sort of surface we're talking about. But let's describe this surface now, because we want to express D, and this whole thing is D. Right, express D as a triple integral using cylindrical coordinates. Okay. Now, to use cylindrical coordinates, we need to describe the region D in set builder notation by using the R theta Z coordinate system. The R theta Z coordinate system is called the cylindrical coordinate system. Right, so in the cylindrical coordinate system, we need to describe now first, the angle theta. The angle theta. Where do we see the angle theta? The angle theta is an angle that is actually determined on the XY plane. On the XY plane. It has nothing to do with the Z plane or the Z axis. But now, if you look at this here, it's a paraboloid. And this paraboloid, it is actually, it occupies the base. So that we're able to see, therefore, that our theta lies between 0 and 2 pi regions. This is a paraboloid. And this top section, it's like it's a circle. Yes, the top section, the top cross section is a circle. So even here, this paraboloid is 3D. So this thing is like a
Sorry,
base.
sir.
Yes, please.
Is it a 2-hour class or?
1 hour. I know that, so I'm gonna stop at 10 past.
Okay.
That's what I.
Yeah, because
Yeah.
you're too fast now. I can't understand.
Oh, is it? Okay, let me slow down a
And
little bit.
before we next time tell
Yes.
me what topics we are going.
Yes, I understand. I'm gonna tell you which topics we're gonna discuss so that you're able to follow. Yeah, I planned 1 hour, so we're gonna finish just at about 10 past. Yeah, I know it must be just a few minutes because I started it at about 8 past 4. So I've planned the time there. Okay, let us slow down. Let us slow down. Right. So in slowing down,